Okay, all right. Hi, this is Oscar, and so today we're going to go over a very small topic that's called the properties of waves. Okay, so there are two types of waves in in real life. So one is called traveling waves, and the other one is called standing waves. We will mainly focus on traveling waves in this topic. So what is the traveling wave? So traveling wave is basically an oscillation that transfer energy without having to pass any matter through. Okay, so it's basically something that transfers energy. But the thing is, the special thing about transfer moving waves is that it can transfer energy without moving the matter through. In real life, we have lots of situations where you can transfer energy to another object by 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 transferring the matter, right? So, for example, if I throw a ball at somebody, then I transfer the chemical energy inside my muscle to the kinetic energy of the ball, and when the ball travels and hit the other person, then energy is transferred, right? All the kinetic energy turn into heat and sound energy when they hit the other guy. So this is what usually energy transfer is like. But for wave, I don't need to move the ball from here to here. All I have to do is to do something that we call an oscillation, which is going back and forth about a point. Okay. And so usually what traveling wave is like is that there is usually a source for traveling waves. Okay. So there is this source that does oscillations back and forth. And what this source does is that when it does oscillations back and forth, it influences the next particle next to it to do oscillations back and forth. And and the next particle, when does oscillation back and forth, it influences the next particle to do oscillations back and forth. And so basically, that's what happens. And this goes on and on and on and on from the source expanding outwards. And this is basically how wave transfer energy. And so in traveling waves, there are a couple of characteristics which or parameters which we must cover. We must define them. Okay. So the first one is what we call displacement. So what displacement is that it is essentially the distance from the equilibrium position. Remember previously where I talked about the uh, wave how waves transfer energy through oscillation back and forth. Well, displacement is in this case would be how far the particle is from its equilibrium position where it goes back and forth, right? So in the previous case, then this would be the equilibrium, right? And whatever the distance a particle is from the equilibrium position, it is called the displacement. And the next thing that we want to talk about is the amplitude. And amplitude is basically the maximum displacement that a particle could go under the influence of a traveling wave. So in this case, the maximum displacement might be this much, right? So this is the amplitude. And it kind of represents the kinetic energy that influences the particle to move um, in the traveling wave. And the next thing that we wanted to talk about is wavelength, right? So when we think about waves in our lives, we usually kind of think about this shape, right? So this is kind of like the similar to a side view of a water wave. And so what wavelength essentially is it's sort of like a section of repeating patterns inside a wave. So you see when you have a wave like this, right? It is essentially multiples of repeating um repeating pattern of this shape. So this is what we so in this case, then we sort of take it as a unit for in terms of calculating in terms of calculating waves. Uh, it's a little bit abstract, right? But we can sort of define it as like um how wide peak and how wide is the distance between the peak of a wave and the next peak of the wave. And so basically this is what we call wavelength. And just for you to visualize it, the amplitude for normal water wave would be this point, would be this much. And okay, right. And the next thing that we want to talk about is period and frequency. So period is basically um, in a given second. So in 1 second, uh, so frequency is basically in 1 second, how many of these wavelengths passes through a certain point? Okay. So basically in 1 second, how many of these oscillations happen? And the unit for frequency, we use hertz. And period is kind of opposite of that, which is in for one of wavelength, for one oscillation to occur, then how long would that need? Okay, and since they're kind of opposite, we can relate them by the formula. Frequency equals to 1/period. And by the way, the unit for period is in seconds. All right. And the next thing that we want to talk about is what we call wave speed. Okay. Since wave is a traveling wave is a form of transferring energy, then certainly we're interested in how fast it is at transferring energy, right? So if I try to transfer energy from a distance a kilometer away from you, then how long would that take for the energy to reach you, right? Which is a kilometer away. And so in that case, we have to know how fast the waves are traveling at. So the general formula for the speed of the wave is velocity equals to frequency times by the wavelength, right? And if you think about it, it is kind of intuitive. So frequency is basically in 1 second, how many oscillations occur, right? In 1 second, how many oscillations occur? And wavelength is basically one oscillation. How long is one oscillation in terms of distance? And so if you multiply these together, then you would kind of get so this is essentially distance, and this is essentially um 1/time, right? So unit wise, you would get distance over time, which is the exact formula for velocity. Now, something that a lot of people get wrong about traveling waves is that they think when you have a traveling wave, particles move along this trajectory. This is not true because think about it. If particles do move along this trajectory, then essentially energy is transferred with matter moving, right? Then there will be no difference compared to when you throw a ball at somebody, right? The matter still goes from here to here. This is so this is not true in the actual case. In the actual case, the particles remain at their position. So for example, the particle would stay at this position up and down no matter how the wave moves. Okay, so even if you see a water wave traveling outwards, ripples outward, all of the water particles, they stay at the same point vertically. Okay, they still oscillate, but it's just that their equilibrium position don't move, so they just go back and forth around the same point. A thought experiment to better understand this would be when you place something on a water wave, um, you would expect it not to move horizontally, but you would expect it to move up and down when water wave ripples outward. Okay, and so this is everything in about the properties of a wave. Thank you.